Hi, we were talking about a magnetic field in a magnetic material. Uh, Today we discuss the Ampere's law in a magnetized material. Okay. If there is a body through which a current J is flowing, this is nothing but the free current due to the conduction electrons flowing through this material. This current produces a magnetic field, and in this magnetic field we keep a magnetic material. Then this is a magnetic material, any kind of material, maybe iron or something. In this magnetic field, our material is get magnetized, which means dipole moments are developed in this material. Therefore, this material is magnetized in a particular direction. M is the magnetization of this body. That is, the free current density produces a magnetic field, and in this magnetic field the material is get magnetized, where M is the magnetization of this body. Okay. In general, we have the equation, that is Ampere's law, del cross B is equal to mu 0 J. In this magnetized material, the magnetization would give rise to volume bound current density Jb. The magnetization would give rise to a volume current density Jb. Jb is the current density developed because of the magnetization in this body. As far as this magnetic material is concerned, now the total magnetic field of this body experienced by this body, that is equal to the magnetic field due to this current and the magnetic field due to this magnetization. Therefore, I can write this B, total magnetic field of experienced by this body, or total magnetic field in this body, is equal to, due to both the free current as well as the bound currents. Therefore, for this magnetic material, now we need to consider both the currents, that is current due to the free current as well as the bound current, which means this J needs to be replaced by this free current plus the bound current. In a magnetic material, J can be written as JF free current plus the bound current. This JF is the current applied from outside. Then you need to put 2 in 1. Then equation 1 can be written as del cross B is equal to mu 0 into, instead of J, substitute this one, JF plus JB. Okay. That is del cross B is equal to mu 0 into JF plus mu 0 into JB. This volume bound current density, we have already derived an expression, that is this JB is equal to del cross M, volume current density because of the magnetization. Therefore, this expression can be rewritten mu 0 JF plus mu 0 into del cross M. Now, if you take the mu 0 outside, del cross B is equal to mu 0 JF plus del cross M or del cross B divided by mu 0. I take mu 0 left side. JF plus del cross M. Now bring this del cross M left side. This del cross B by mu 0 minus del cross M is equal to JF. From this, you can take a del cross common outside. This is B by mu 0 minus M. This is free current. This equation is very similar to the equation we wrote in the electric polarization. That is del, where we have written del dot epsilon 0 E plus P equal to rho F. That is the case of electric polarization. This is in the case of a magnetized material. This is a electrically polarized material. In electrically polarized material, we have taken this as a D, that is electric displacement vector. This electric displacement vector, therefore we have written this expression del dot D is equal to rho F. This electric displacement vector is an auxiliary vector or auxiliary field. This D is not an electric field. It is not purely an electric field, but this is related to purely on the free charge. Okay, that is the D is related to the free charge. In the similar way, if you look at this expression, that is del cross B by mu 0 minus M equal to JF. This expression, this is another oscillatory vector. I will call this vector as H. This H is called an oscillatory field or oscillatory vector field. Therefore, this expression can be written as del cross H is equal to JF, where H is equal to B by mu 0 minus M. Okay. Here you can see that it is similar to the D, where D depends purely on the free charge density. Here the auxiliary vector or auxiliary field H purely depends upon the free current. This can be written as H is equal to B by mu 0 minus M. This B by mu 0, if I take it to left side, this will be H plus M, or this B can be written as mu 0 into H plus M. If you have a free current flowing along this direction, then that produces a magnetizing field H, and if you keep your material, magnetic material in this field, magnetic dipole moments develop in this material, this would give rise to a magnetization M. Therefore, the total magnetic field density in the material, that can be written as B. That B is a sum of M and the field H. It is mu 0 into H. Okay, right. B is equal to mu 0 into H plus M. This is the total magnetic field density of this body. Now we can say that this H is the magnetizing field. This arises from the free current density JF according to this expression. This magnetizing field magnetizes this magnetic material. Therefore, this material gets another magnetic field due to this magnetization. Or we can say this total magnetic field density or total magnetic field of this body is equal to sum of this magnetizing field H plus the magnetic field due to this magnetization. Therefore, this H can be written as applied external field, or this is a magnetizing field. The M is a magnetization or the field due to the magnetization, and this B is a total magnetic field, magnetic flux density. Total magnetic flux density. M is a field due to the magnetization. Therefore, for a magnetized material, we have these expressions: del cross H is equal to JF, and also the del dot B will be 0. This is for a magnetized material. These are very similar to the equation we had in electrostatics in the case of electric polarization. It was del cross E is equal to 0, del dot D is equal to rho free. This is a electric polarization. This is the case of magnetic material, magnetized material. And also it is to be noted that this del cross H is equal to JF, that is a Ampere's law in a magnetized material. Says. Now let us see what is the integral form of the Ampere's law in a magnetized material. This is we discussed integral form of Ampere's law in a magnetized material. We have the differential form, that is del cross H is equal to JF. Now we do the surface integration of this equation, that is surface integral del cross H dA. Do the same operation on the right hand side also, surface integral J dot dA. You know that this J is nothing but di by dA, or di is equal to J dot dA, or I is equal to J dot dA. Or I can write this is the total current. Total current means it is a free current, IF. Therefore, this can be written as del cross H dot dA is equal to IF. Here I apply Stokes theorem. That is line integral H dot dl. This surface integral can be written to line integral. Then that will be equal to the IF. This is the free current enclosed. Okay. Or this is the total current flowing through the Ampering loop. And we can say this is a integral form of Ampere's law in a magnetized material. can say this is a total free current flowing through the Amperean loop. Total free current enclosed by the Amperean loop. The conclusion is the differential form of the Ampere's law is del cross H is equal to JF. The integral form of the Ampere's law is H dot dl is equal to IF. Now let us discuss magnetic susceptibility. This means how susceptible the magnetic material for the applied magnetic field. It is denoted by chi m. The similar notation we have used in the electric field in matter chapter, that is chi e, that was electric susceptibility. How susceptible the material for the applied electric field. That is, here the case is a magnetic susceptibility. That is, if I apply an external magnetic field H, and in this magnetic field, if I keep a magnetic material, maybe an iron piece, this magnetizing field magnetize this material, which means magnetic dipole moments are developed in this material. That magnetic dipoles would give rise to a magnetization M. That is, the amount of magnetic dipoles developed per unit volume, or the magnetization, that is proportional to this H. M is proportional to H. Or this M can be written as, if I replace its proportionality by equal sign, introduce a constant, that is chi m into H. This chi m is the magnetic susceptibility. Okay. Which means this chi m can be written as m by H. That is, which means how susceptible this magnetic material for the applied magnetic field. The susceptibility will be different for different material. In the similar way, we will discuss next topic, that is magnetic permeability. We have the expression for the total magnetic flux density in this material, that is the sum of the magnetizing field, because this magnetizing field is also passing through this material. This magnetizing field H plus M, that we have written B is equal to mu 0 H plus M. Here, from this expression, we have this M is equal to chi m H. Then substitute this M to this expression, that is mu 0 H plus chi m H. That is, this B is equal to mu 0, take H outside, 1 plus chi m. Magnetic field B can be written as mu H. This B can be written as mu into H. Okay. Where mu is the permeability of this magnetic material, or the permeability of this medium. Now, if I substitute this quantity here, this equation will be mu H is equal to mu 0 H into 1 plus chi m. This H and H cancelled. If I take mu 0 left side, mu by mu 0 is equal to 1 plus chi m. This is one relation that it connects magnetic susceptibility to the magnetic permeability. Okay. This quantity mu is called magnetic permeability of the medium. We have seen the similar relation like epsilon by epsilon 0 in the case of electrically polarized material, that was defined as the dielectric constant or relative permittivity of the dielectric material. Similar way, here we can write mu by mu 0 as a relative permeability. That is, this can be written as mu r is equal to 1 plus chi m. This is a relation connecting relative permeability and magnetic susceptibility. That is, mu r is a relative permeability and mu is a magnetic permeability of the medium, simply the permeability of the medium.